Hi everyone, in this video we're going to discuss triggering. It's one of the most poorly understood aspects of ECU configuration, and I would argue it's probably the most important one to get right. It can cause the most engine damage if it's wrong. So the first thing I always say as an engineer is make sure we understand the objective. What problem are we solving? What's triggering actually there to do? And the point of triggering is for the ECU to know the angle that the engine is at the moment. The more accurately it knows this, the more accurately it can fire the ignition at the right time, and the closer the engine can run to the ragged edge. Ideally, it would work out this information as quickly as possible from when you start cranking, so that it can go nunit vroom instead of nunit vroom. Now, the way that the Adaptronic modular ECUs represent triggering is by recording a current engine angle, which is tracked over a 720 degree period from minus 360 to plus 360 and then straight away back to minus 360 again. 0 is defined as being TDC ignition of cylinder 1. For two-stroke engines, including rotaries, the ECU still tracks the engine angle over a 720 degree period, but it fires the injector twice and the ignition twice during that period. We have several pre-configured triggers for different engines, so if your engine's listed here, then start with that. Start with a base angle of 0 degrees because that's what we set it for, and then fine-tune the ignition timing using a timing lock when the engine's running. This article is mostly about the generic trigger mode, so if you've got a multi-tooth pattern that's not covered by one of our pre-configured triggers. In this mode, you'll need to configure it yourself based on your knowledge of the trigger pattern on the engine. There are several variables that need to be known, which includes the angle increment, the base angle, and the reset types. First, we'll discuss wiring and different sensor types. The first thing that I need to point out is that we need to have the highest tooth count input, which is the one that we'll use for ignition timing and everything else, wired to CAS input 1. For example, if you've got a Toyota distributor with 24 teeth in it, then the 24 tooth input is the one that would connect to CAS 1, which is a GE signal, I think they call it. Similarly, if you've got 12 teeth on the crank, that's the one you'd use for CAS 1. 36 minus 2, again, that's what you'd use. Another example is the Mitsubishi Mazda type sensor, where you have 4 teeth on one sensor and 2 teeth on another sensor, as used on the NA MX-5s, 4G93s, and some of the early 4G63s. So for this sort of sensor, you'd connect the 4-window one to CAS 1 and the 2-window one to CAS 2. For the Nissan optical style triggers, the ECU actually automatically works out which one it is because the wiring changes between different versions of the cars. But if it weren't, then you would need to connect the 360 window input to CAS 1 and the 4, 6 or 8 window to CAS 2. Secondly, there are broadly 2 types of sensors as far as the ECU is concerned electronically. One of them is the variable reluctance sensor, also called VR, reluctor, or confusingly magnetic sensor. Now, these sensors have 2 pins on the sensor only. The sensor's a coil of wire, so you can actually measure the resistance between one pin and the other. It also has an internal magnet. Now, when a tooth passes the front of the sensor, that creates a change in reluctance, which changes the magnetic field strength, which creates a voltage in the coil of wire. The faster the tooth passes the sensor, the faster the change in magnetic flux, and therefore the higher voltage is produced by the sensor. So these sensors, when an engine's spinning at, say, 6,000 RPM compared to 3,000 RPM, generate double the voltage. So the ECU has to be able to handle a high voltage and also the fact that the voltage changes. And another corollary of that is that if the engine's stationary, that is the speed is 0, then you don't get any voltage at all from the sensor. So you don't actually know whether the tooth is facing a sensor or not unless the engine's actually turning. So you can't, for example, turn the engine over by hand and count the teeth by looking at the output of the sensor. The other thing to be careful about is that polarity is important with reluctor sensors. The voltage should increase as the tooth approaches the sensor and then dive down through 0 to a negative value, with 0 being when the tooth's in the middle of the sensor, and then it should recover back up to 0 as the tooth recedes from the sensor. With a missing tooth trigger, you may not be able to tell the polarity except by looking at the gap where the teeth are missing. So in that gap, the voltage needs to rise slowly from negative to the positive because it's the negative transition through 0, which is where the ECU is triggered. Now with a multi-tooth trigger with no missing teeth, then there is no gap to be able to determine that. So what you need to do is make sure that the relative angle between the CAS 1 falling edge and whatever resets you have on CAS 2 or CAS 3 give you the correct amount of margin. You can tell both the reluctor polarity and also the timing margin using the built-in scope in the ECU. The other type of sensor is a digital sensor. These sometimes are optical, but more commonly they're Hall effect. In some cases, there might also be a reluctor sensor which has its own built-in sensor conditioning circuit which gives a digital output. But in this case, the sensor can be easily recognised because these sensors all require power, so they all have at least 3 pins, and the output just pulls to ground when the sensor is being triggered. Therefore, there must be a pull-up resistor inside the ECU. For both the reluctor and the digital sensors in the ECU, you can adjust the voltage at which they're triggered. If the voltage is too low, then it's going to trigger off noise and be susceptible to ignition interference or even triggering when the engine's not turning. If it's too high, then it's not going to trigger sometimes when it needs to, and you're going to miss pulses. This may cause, for example, difficulty in starting. This threshold can be adjusted against RPM, because as we said before, the voltage of the reluctor changes with RPM, and the ECU can also be set to work out the trigger voltage automatically. And that's what we recommend, unless that doesn't work for your particular sensor. So in the generic trigger mode, the first thing is we need to select that it's a generic trigger mode. And next you can select each of the inputs and select whether they're digital or reluctor inputs. If you're using a digital sensor, you need to select whether you're going to trigger off the positive or the negative edge. If you don't know yet, then select it as negative, and we'll check it with the built-in scope. We also, as I said before, recommend selecting the automatic threshold voltage option. The next feature is the filtering. In general, you probably won't need to change this. Normally about 20 microseconds is a good duration because that filters out pretty much all the ignition noise. But on very high tooth count engines like the Nissan optical sensors, at high RPM you'll need to reduce this down to about say 4 microseconds or so. So that's 4 microseconds at about 8,000 RPM. Now we'll look at how the ECU actually handles these trigger events. The first setting we need to consider is the angle increment. So this is the crank angle in degrees between each CAS1 trigger event. For example, if you have 12 teeth on the crankshaft, then the angle increment is going to be 30 degrees, which is 360 divided by 12. If you have 60 minus 2 on the crank, then the angle increment is going to be 6 degrees, which is 360 divided by 60. If the spacing is uneven, that is you have teeth at odd angles, not counting missing teeth, then you're going to have to use a dedicated trigger mode set up for that pattern. The next thing to consider is how the engine actually knows where top dead center is, or if you like, where to start counting from. There'll need to be some sort of reset event which happens every 1 crank revolution, or cam revolution, or both. So if there's a missing tooth on the crank, then we're going to need to use that as our TDC reference. So in that case, we're going to trigger 1 and select crank reset as the reset type, and select either 1 or 2 missing teeth depending on how many missing teeth there are. In this case, the angle before top dead center when the first tooth after the gap is lined up with the sensor. Now, being a 720 degree cycle, this is going to actually occur at 2 values, or at 2 times within that 720 degree cycle. So 1 value, and then there's the other value, which is the first one, plus 360 or minus 360 degrees. So at this stage, just select the value that's closer to 0, and if it's wrong, we'll change that later. The other common case is where you have a multi-tooth on the crank and a single reset on a camshaft. In this case, you'd select the reset type on CAS1 to be none, and CAS2 would be cam reset, but you'd select the type to be every tooth rather than on a missing tooth. When you line up the cam tooth with its sensor, if you rotate the engine forward so that the next crank tooth is opposite its sensor, what's the current angle of the engine in degrees before top dead center? Or if you like, how many more degrees does it have to turn through to get to TDC from that point? Now, if the reset is on the crankshaft rather than on the camshaft, for example on the RX-7 FD, or if it happens twice through a cam cycle like on the FC, then you need to select the reset type as being crank rather than cam. Now, if you're using a trigger type which has a multi-tooth on the trigger and a single cam tooth, then you need to make sure that you've got the correct polarity on the crank sensor, or if you're using a digital sensor, that you're using the best edge for that. Now, the way to do this is to look at both of them on the built-in scope. You can see where the cam trigger actually is triggered, and you need to make sure that the corresponding CAS1 input is as far away as possible from that. So if they're lined up, that's the worst case, and if the reset happens halfway in between 2 crank teeth, then that's the best case. So if they are perfectly lined up with the reluctor sensor, then it means that your reluctor polarity on CAS1 is wrong. Now, if in the setup that you've done so far, you only have selected a crank type reset and there's been no cam type reset, then the ECU doesn't have 720 degrees worth of information. It only knows where it is within a 360 degree cycle. Now, on a 4-stroke engine, best results will be obtained by giving the ECU 720 degrees worth of information. So that means either that you need to use a cam sensor as well, possibly add one, or if we haven't configured it yet, then we need to. So if it's a single tooth on the camshaft and you're using, say, a missing tooth crank reset, then select the reset type instead of being CAM as being first half only, and still reset every tooth. That way the ECU isn't going to use that tooth to know where TDC is, it's just going to use that tooth to say which 360 degree half of the 720 degree cycle are we in at the moment. Now, a fairly popular method on the Toyota 4-cylinder engines is to have 4-1, so 3 teeth and then a missing teeth, so 3 teeth spaced at 9 degrees on the camshaft. And that way, if you had that sort of an engine, for example on the 2ZZ or the beams, you would select reset type as being first half only, but instead of selecting every tooth, you would select reset on 1 missing tooth instead. So to use this, obviously you need to have a crank reset as well, so that the ECU knows where TDC is. Now you can use the built-in scope not only to look at the trigger inputs, but also to verify that the ECU's understanding of the current engine angle is correct. Now, as you can see in this example, the current engine angle goes up in steps, from -360 up to +360 and then back down again as the engine rotates. And each step corresponds to a new angle update that we get from the engine when we get a CAS1 trigger event. A typical scope settings that you'd use when cranking would be CAS1 inst voltage at 1 volt per division, CAS2 inst voltage at 2 volt at 1 volt per division, and current engine angle at 100 degrees per division. You may want to see RPM as well, it's up to you. And time-based normally would be about 50 milliseconds per division, maybe 100 milliseconds per division if you want a bit more context. Now, once you have the correct triggering, then you should be able to see this current engine angle going up in steps once it's actually synced up, and the RPM should be stable. The other setting that must be set correctly is the RPM cranking threshold. This must be higher than the actual cranking RPM with a bit of margin. So for example, if your engine cranks at 240 RPM, then you'd probably set that to 300 RPM or something like that. Once the RPM exceeds this value, the ECU will go out of cranking mode and start doing the post-crank enrichment, jump into the main fuel map and so on. And if the RPM ever falls below this value, it'll go back into the cranking mode. Now the final thing we need to discuss with respect to triggering is variable valve timing inputs. So the ECU always records the trigger angles of every input other than CAS1, because they're the ones that you'd be using for VVT. So it always records the trigger angle events of CAS2, CAS3, and if you've got a mini real-time module installed, CAS4 and 5 as well. Now for digital triggers, you'll need to select the correct edge, either positive or negative edge, so that you get stable VVT readings. Now the last point I need to discuss is when you actually are setting up the engine, how do you know whether TDC according to the crank pulley is the TDC of cylinder 1 ignition or cylinder 1 overlap, that is between intake and exhaust. Now if you've got exposed cam pulleys, then often there are markings on there and that will tell you. Another way that you can do it is you can remove a spark plug and put a hose on the plug hole and try and blow into it and see if the valves are open or not. If they're not, then it's at TDC ignition, and if they are open, then it's going to be at the overlap period, so between the exhaust and the next intake stroke. But my favourite way, which I like because I don't like getting my hands dirty, is to actually start the engine off in wasted spark mode. So if you've got a direct fire engine, then you can go to the ignition output section and tell it to fire every 360 degrees instead of every 720. That way the ECU will be referencing the engine angle over a 720 degree period. It'll fire the ignition twice. So that way the engine will still run even if it's out of phase by 360 degrees. Now while it's running, if you change the ignition output pattern to 360 degrees instead of 720, if the engine continues to run, then you know that it must be right. Now if the engine stalls, then you know that it's out by 360 degrees. So change the base angle by 360 degrees. For example, if it's 90 at the moment, then make it -270 or make it +450, that's the same thing. Then you can start up again, repeat the experiment, verify that the engine keeps running, then you're set. Now the last thing which I really like to do is if you're using a missing tooth crank reset and a separate first half only cam reset, what you can do is you can tell the ECU to fire the ignition output's wasted spark until it gets the cam trigger and then switch over to direct fire. So to do this, set the ignition output mode to be 360 degrees until we get cam information, then switch to 720, and that way it doesn't need to wait for the cam trigger to be able to fire the engine. And that gives you unit vroom sort of OEM level starting performance, which I like because I'm impatient. I don't like waiting for engines to start. Thanks very much.